validation set.
Okay.
So, hi, it's my pleasure to welcome Professor Giuseppe Giacomo from the University of Roma La Sapienza to ISI, and we're happy he's going to give a talk with little research. So Professor Di Giacomo is a AAAI fellow, ACM fellow, AI fellow, so fellow of the European Artificial Intelligence and Association for Advancement of Artificial Intelligence in the US, and has done a lot of work in knowledge presentation, AI planning, data integration, has a large. He also was instrumental in this in data integration, in the ontology-based data access, and using ontologies to integrate data. But today he's going to talk about some new project that he's really excited about, which is the white box self-programming that is related with AI and knowledge presentation. And welcome. Thank you.
Thank you very much. So I would like to keep this very formal. Stop me every moment you like, for whatever you like. If you get bored, tell me. If you are going too quickly, tell me. I have 68 slides, but I don't have to show all of them. Okay. So the first thing I want to talk a little bit about, is the idea behind this project. And I'm going to show you this idea through an example. And the example is the following. Actually, the example comes from something that has happened in reality, okay, although there was no AI involved in the reality case. So after a long weekend, human supervisor inspect a manufacturing system, a factory, and notices that the production has slowed down a lot, okay, but is still producing. Okay? So she queries the system on what it's doing. Okay, so she queries the behavior of the system, and the system says to her that it revised the process by avoiding the production island 176 by repurposing the tools in another production island 176671 and sending items over there. She then queries why the system reprogrammed itself to do so. Why? And the system answers that on Sunday at a certain time, this production island started to produce an acceptable percentage of defective items, and based on the test performed during production, and so the system restructured the process to achieve the specified objective, quality and throughput, as much as it could, actually, in presence of the faulty island. And to do so, it shut it down, so to avoid to shut it down the production line. The system analyzed what were the island, the capability, the resources available, and decided to reprogram itself in this way. Now, in the actual case, the production went on. They produced zinc for a weekend, so thousands of zincs, all with a certain error, and they have to throw all of them away. Okay, so this is a process. That has sensing and acting capabilities. Okay, now obviously sensing and acting capability, they call for AI. On the one hand sense, they call for AI because of sensing and acting may require advanced sensing techniques like machine learning, but also because we actually had to decide how to act. Okay, and this is the focus of this talk. The process could monitor and detect faulty execution, and notice that it is getting rich data about this process. This data, rich data means they are not going to be proposition, they're going to be relational. They're going to talk about objects and the relationship between these objects. So this is going to be a sort of first-order state description of the system. And the process has self-deliberation, self-programming abilities, and it could modify its logic, the logic of its behavior, without human intervention. And finally, very important, the system can be queried to ask, can be queried, obviously, can be queried to report on its behavior and why it did certain decision. Now, when we say query, here immediately one can think about having a query maybe in natural language, having somehow a good interface toward the human. But here I'm talking about something a little bit more basic. Query for me means being able to verify its behavior. So having the tools to then have a natural language processing over it. Okay, but I'm really interested in see what property the behavior is enacting in general, not for human for direct human casual user understanding, let's say. Now, this setting that I showed actually is important in several application domains, for smart manufacturing, obviously, but also for Internet of Things. In particular, when I talk about Internet of Things, I'm especially referring to making a smart space, a space smart, and the kind of space I'm interested in are public spaces, so not your home, where everything is somehow controlled, but maybe a hall or a museum or a square, okay, where many people come in, go out, each home with its own goals, etc. And the system somehow has to react in a good way to what's happening. And also into business management. What is business process management? So this is a discipline that is actually advocating for a conceptual description of the process, okay, that is then available to the organization, and the organization can look at the process and decide if it can be improved or not. And this is obviously a very important area, and we all know about SAP and other tools for workflow processing, but it's becoming scientifically pretty interesting. And here I have some example. For example, in smart manufacturing, what we have just seen is an example of how it can be used, but let me show you, for example, one in Internet of Things. So here we are in a museum, a smart space, and we have a temperature, a humidity of museum rooms at a certain desired level. At a certain point, a very large crowd comes in a certain room. Okay, this is not known a priori, because if it's known a priori, you already know how to do it. Okay, but somehow, for some strange reason, too many people are inside the room. And now you see that this system actually repurposed the secondary air conditioning system that normally is used when the first one fails. Okay, so it started together with the first one to keep things in the safe boundary, the parameter of humidity and temperature in the safe boundary. Okay, and this is completely unanticipated, so it's really done on the fly. And on process management, suppose you have a new privacy regulation, certain data cannot be kept anymore, so the process tries to see if it can change itself to avoid keeping this data, okay? So these are all cases in which the system somehow automatically reprograms themselves. So we are interested in a new generation of dynamic system, essentially led by AI, and dynamic systems that don't need to be explicitly programmed, but learn and reason from the interaction with humans and interaction with the environment. And obviously, there is a lot of literature in autonomic computing, how to do this kind of self-programming techniques. But actually, these self-programming techniques are always somehow predefined. So they have very good methodologies in order to somehow build a very general program, but the logic itself is always already given by the programmer. It's not synthesized on the fly. Okay, instead here we want to synthesize it on the fly. Obviously, these things start to program themselves, and it becomes very important to be safe on these things, because these things can change their behavior. And maybe the most important quality is to be able to query. So querying these things were quite important in order to be sure that we can trust what the machine has done. And in all this example, there was some sort of queryability. And obviously this queryability is very related to transparency, accountability, explainability, and is advocated by a large part of the AI community, the computer science community, and also Europe in particular has a certain roadmap for AI in which trustworthy AI is at the center really of the plan. Okay, in order to do this kind of things, this kind of mechanism, this kind of self-programming mechanism, white box self-programming mechanism, obviously we have to touch many areas, many items. So we need to program this to equip this mechanism with self-programming abilities. We need to make these self-programming abilities analyzable and comprehensible in human terms. And again, this is the queryability of the system. We need to make the self-programming mechanism data aware. Probably we want a component-based approach in order to be able to scale. And obviously we want to integrate this model-based AI that is in these 4 items with a model-free AI or and the integration of these 2 things is a little bit probably one of the most interesting issues in AI. Okay, in this talk I'm going to focus only on self-programmability, and in particular I'm going to focus on the fact that planning in AI and reactive synthesis in formal methods, when merged in a certain way, are giving us a jump in the capabilities of planning. So let me go through it. So self-programmability, we need this mechanism to adapt themselves to new unexpected conditions. And there is an area of AI that looks at these kind of things, and this is planning, which is considered one of the central areas of AI for developing intelligent and autonomous systems. And planning is a good candidate for very many reasons. Okay? And the reasons are the following. First of all, in planning, we do have a model of the world. Okay? And what is the model? The model is the domain. So you have a description of the world in terms of what are called fluents that are describing the state, how the state of the world is in a certain moment, and actions that allow you to change the state. So this model is a very important thing because actually this model allows us to query what's happening in reality, through the model. We can ask the model. Then we have solver. We have very good solvers for planning, very good solver, and they actually are able to solve essentially a set of problems. One is reachability, classical planning. Then we have adversarial reachability. This is planning in non-deterministic domain. Adversarial reachability under fair assumption, okay? If we think that the non-determinism depends on probabilities, okay, even if unknown. And also these solvers can also be adapted to solve the dual problem of reachability, which is safety, which is never go to a failure state. So stay in the safe area. Okay, you can use the same algorithm essentially. So there is an entire community working on these solvers. So this is a very good thing. Okay, these solvers are actually, they scale, they are in very good, in a very good situation. They are improving year after year, and it's a pretty exciting time for planning. Models make planning human comprehensible. This model and the plan themselves can be queried. Okay, how? You can ask to verify certain temporal properties, certain dynamic properties. Okay, through verification, through model checking. And this thing can also be used for explanations. And there is an entire industry now working on explaining planning. But this kind of explanation is not the queryability. Queryability, it's obvious in the case of planning. This kind of explanation is, what should I tell you, okay, of this complex property that I'm checking? Okay, I want to tell you only very few things because I don't want to flood you with a lot of information. So this is more for the casual user, but for the engineer, this is really what is needed, right? The ability of querying what the plan does. And obviously, planning can also be used for doing what is analysis. You can check different things. You can check a little, change a little bit the model. You can change a little bit the goal. And this would give you several opportunities of looking at what would be if something was to counterfactual, right?
So in the planning community, the reachability is usually the efficiency for it comes from a tight over-approximation. Is this correct? Over-approximation of what is reachable and what is not.
You mean for heuristic? So
for example, if you look at the planning graphs that do the reachability analysis, they are very good estimates, but they're always sort of a little bit over-approximations.
Yes, so these are heuristics, no? So they do heuristics. Heuristics tell you where to go. Okay, what is the best, most promising path? And one of the most used heuristic, for example, is the removing all the negative information so that you have only positive. Not all of these things will work on a more general setting. We have to be very careful. And indeed, while some years ago, this idea of removing all the negative information looks like panacea or planning, I don't think that this is the case nowadays. Okay, so the heuristics are much finer than that. However, planning has also several limitations, need to be extended in several directions. Okay, so the first direction is the goal. So the goal in planning is reach a state of affair. So it's reachability. Get to a moment in time in which a certain thing is true. But what about the process to get to that moment? Okay, so while you're getting there, do you want certain things to be true? Do you want certain phases? I don't know, every time that I cross a door, I want to open it and then close it because I want to keep everything in order? Or do I want to do many things? So maybe first get a cup of coffee and then go to the door and then go to the office of somebody else, etc. And now, if I have many of these things, one after the other, this would actually change how you do the planning. So here, there is something from formal method that helps us. In formal method, they always talking about this property, this dynamic property. And what they do, they use temporal logics. So what we would like to do, we would like to have goals that are temporal logic specification in general, not only of the kind eventually get to this state, but any arbitrary thing. Every time that something happens, in a finite number of steps, something else must have happened during the plan, okay? And so on. The other thing is that the model is true. We have a model, but the model is very tight. In particular, first of all, it's Markovian. Given the state, given the action, new state. Not everything is like that. Maybe you need to consider the entire history, okay, or fragment of the history, okay, non-Markovian domains. And the other thing is, in planning, the state is represented propositionally, but we want it to be relational in general. And when you go to relational, planning has not much to say because it requires you to first propositionalize and work with propositions. And then there are other things. Now, this related also to psychology. So where do the goals come from? Okay, so the goal, obviously, in most of the cases, will be given by humans. Okay, but is this always the case? Maybe not. Maybe sometimes the planner itself, the agent itself, wants to formulate its goal. Okay? And obviously, if we change in this direction, the algorithm also will need to change. And for many of these things, not for this one, but for many of these things, formal methods can help. Now, this slide is possibly the most important slide of this talk. So it essentially shows you, on the one hand, what is planning, and on the other hand, something that is very related to planning. This is called reactive synthesis. It is very well studied in formal methods. Let's go through this together. So in planning, we have fluents that are controlled by the environment, and action that are controlled by the agent. So you do the action, the environment answers with the effect of the action. If the environment is non-deterministic, actually the environment chooses the effect of the action. Okay, maybe it chooses probabilistically, but actually it's the responsibility of the environment to come up with the answer in terms of fluent to an action. Then we have a planning domain. What is a domain? It's a description of how the world works. Okay? And this is used by the planner because the planner will make its plan work only assuming that the world is working according to the domain. Okay, if you change the domain, your plan will not work. This is pretty interesting because the description of the domain is typically pretty large. Okay, it's pretty several pages. Okay, thousands of lines in PDDL. Instead, the goal is very small. Okay, typically it's just few lines. And maybe this distinction is very important that makes the description of the assumption you can have when satisfying a certain goal explicit. Then we have the goal. The goal are propositional formulas. Then in planning can be seen as a game between two players. Okay, one player is the environment, and the other player is the agent. They play over a certain arena. The arena is the domain, gives the rules that everybody has to satisfy. And the game is the agent tries to force eventually reaching the goal, which is a propositional formula, says only that certain things must be true eventually, no matter what the environment does. Okay, in spite of what the environment does, the agent is able to force whatever the environment does, the satisfaction of eventually the goal will be true. This is planning. And planning is actually generate a strategy that does this. And this strategy, notice it's a function. It's a function that looks at the history of the fluents, the value of the fluents, and decide the action. And the function wins the game if when paired with any possible answer of the environment, will complying to the domain, will actually get to the goal. This is planning in fully observable non-deterministic domain. This problem is extent complete, but we have very good algorithm for computing this. Okay, so extent is not a problem. So this complexity, so we have been trained to think that this complexity is somehow can be a guide to decide what can be done and what cannot be done. Unfortunately, this is not at all the case. Okay, so complexity talks about the worst case. In AI, there's nothing that is not exponential. Okay, maybe you can be NP, okay, but at least NP you are. Okay, and the fact that it's time is not really that crucial. I think that is crucial is if we have good algorithm. What it means good algorithm? Algorithm that find the easy solution first, and then go to X time when there is really nothing to do. Okay, because the problem is X time hard. So we know that there are instances in which we need to do an exponential computation, but not all of them. Now let's go to the reactive synthesis. Reactive synthesis, instead of fluents, we have inputs. These are controlled by the environment. They're called inputs. Instead of action, we have outputs. Okay, outputs, why? The domain does not exist. Everything is put in the formula. Okay, and the goal is an arbitrary LTL formula, an arbitrary temporal logic formula. Okay, so if you want to put the assumption, you put it in the formula. Okay, oops. You put it in the formula. The arena, the result of this is that the arena is unconstrained. We don't have any arena. The players, we have still agent and environment as before. The game, the agent has to force satisfying the entire LTL formula in spite of what the environment does. Winning strategy has exactly the same shape as in planning, okay? And algorithms are 2x time. Okay, 2x time, this is really too much. Again, the problem is not 2x time. There is a much bigger problem. And the problem is that these algorithms that we have nowadays are not scalable. Okay, so they fail on easy cases, not on difficult cases. On difficult cases, we expect to fail. But they fail on easy cases. And there is a very specific problem here. And the problem is that given LTL formula, you want to transform it into an automaton, make it deterministic, and then take this deterministic automata and play the game over this deterministic automata. Okay? Unfortunately, this is infinite trajectories. Okay, so the automata is a non-deterministic Boolean automaton. Determinizing non-deterministic Boolean automaton is one of the most difficult things that are there in computer science. Okay, it's an unsolved problem. In the sense, it is solved. We know how to do it. Okay, we know how to do it optimally with respect to complexity, but we don't have any good algorithm. So what can we say? We can say reactive synthesis is a fantastic theory. Okay, it actually developed this in details. We're using very good mathematics, really much better, I would say, than planning. However, we have no actual algorithm for doing it. Okay, so it's a beautiful theory, but impractical. For this reason, some years ago, we were discussing these things with Moshe Vardi, and at a certain point, we started thinking, why don't we do reactive synthesis on finite traces? Okay, so what it means, instead of using LTL, or temporal logic, we use temporal logic over finite traces. What it means that we don't think now time to extend to the infinitum, but we think that time will end when the goal is fulfilled, let's say. And you are interested in what happens from the start to the end. Okay, so the finite trace. And this concept actually in AI has come up many times. Many times, if you look at the literature, there are many times people were using temporal logic for doing things, but actually they had an interpretation that was finite traces. And by the way, this has been a source of all sorts of errors. If you are curious, you can look in the literature, 2014, 2012, you'll find some paper that shows that what is done typically, I don't know, in PDDL3, where that is the planning formalization of linear time logic, is wrong. Okay, is literally wrong. So what is described, how you should proceed to do the algorithm, to actually execute the algorithm that says, go to the Bookie automata, make it, fake it as it was a non-Bookie automata, but a standard automata, then determinize it. This is wrong. Okay, you cannot do that. Okay? But people understood this much later. Yeah. Okay, so I'm going to talk about I'm going to mention two variants of linear time logic on finite traces. The first is really linear time logic. Okay, exactly same syntax, identical syntax to linear time logic. So you have the Booleans, proposition, Booleans, next, until, eventually, always. Here, since the trace ends, you have also last. And actually, you have two kinds of next. You have next, the standard one that says there exists a next time point, and in that time point something will be true, and a weak next one that says if there exists a next state, something will be true. Okay, because this weak next, often written with this black circle, doesn't exist in LTL, because we know that every instant of time has a future, because it's infinite. Okay, so what we know about this logic? We know that its expressibility is very well characterized. It captures everything you can write in first-order logic over finite sequences. Okay, everything you can write in first-order logic over finite sequences, you can write it in this logic. And we know to do satisfiability, validity, entailment, all p-space complete. Model checking, also p-space complete. Actually linear in the transition system and p-space complete in the formula. These are exactly the same properties that we have in LTL on infinite traces. Okay, they're not mentioning synthesis yet. Okay. LDL instead replaces this temporal operator with two temporal operators coming from dynamic logic. One says there exists a trace satisfying a certain regular expression, a certain regular language that ends in a state where phi holds. This is the diamond. And then the box is all the traces of a certain regular language end in a state where a certain formula is true. The box. What is the characteristic of the syntax is that of dynamic logic, but the characteristic is this capture monadic second-order logic. Okay, they are expressive monadic second-order logic. This is essentially the most expressive decidable logic we have on finite strings. Okay, for the rest, they have exactly the same property as LTL, so it's only a little bit more general. Now, there are many LTL formulas on finite traces that are important. Okay, and in particular, there is the catalog of formulas that you can read on. And it's interesting. Well, no, let me say this later. And you can capture easily linear time logic in a linear dynamic logic. For example, here, you say every time that there is a request, eventually you get coffee, can be written in this way. But what's interesting about this possibility of using regular expression is that in AI, these regular expressions are called programming schemas, and they've been studied, okay, with logics like situation calculus and in particular languages, programming language over situation calculus. And obviously they can say things that are pretty strange. For example, here, while hot, if the air conditioning is off, then turn the air conditioning on, else keep it off, and allow some other things to be done at this time point. So you can say things that must be true while you're doing other things. And here there is a connection with Golog and situation calculus. In particular, we can really take Golog over a finite domain of object, and every Golog program can be actually translated into this kind of regular expression and can be translated into ADL formula. So this makes them particularly interesting from the knowledge representation point of view. Okay. The point is that this logic can be translated into automata. So every time that you have one of these formula, this formula defines a language, all the traces that satisfy the formula, and this language is actually regular. Okay? What do you mean it's regular? It means these are now using the automata that we all know. Okay, not the automata on infinite traces. These are the automata on finite traces. Okay? And each of these formula just capture one of these automata. In particular, we can compute this automata, and the way to do it essentially is the following. We can compute the non-deterministic automata corresponding to every formula. Essentially, we have a set of rules, okay, that decompose the formula. Okay, this set of rules give rise to what is called an alternating automata, but we don't even need to know what it is. These are just rules that decompose the formula, and then we have an algorithm that, making use of these rules, generates the non-deterministic automaton. And this procedure is exponential. Okay, and gives rise to a non-deterministic automaton. If you have a more complex language, like ADL, well, the algorithm is exactly the same, but the set of rules is now a little bit different. Okay, and this algorithm, by the way, is essentially the standard algorithm to transforming alternating automata into automata. You don't even need to know it, but if you want to. Okay, how big are these formulas? They are, in many cases, very small. Okay, in many cases, very small. Okay, obviously, they can become exponential, but in many cases, they are not. For example, for eventually, this is the automaton corresponding to it. For always, this is the automaton corresponding to it. For every time A is true, then next eventually B will be true. This is the formula. This is the automaton. Often, these automata are very small. And if you look at the catalog that I showed you before, for all the catalog, the number of states that the automata needs is less than 10. Okay? It's typically 1, 2, 3, 4, 5, very small. Okay, so now I'll tell you how to do reasoning on all these things. Satisfiability, you take the formula, you're converting it into into a non-deterministic automata, and you check this automata for non-emptiness. What it means, by the way, checking for non-emptiness? Checking reachability of a final state. Okay? If you can reach for the initial state, the final state, it means at least the word is accepted. Okay? And this is how you do it. The computation is exponential, okay, but can be done on the fly. The checking is logarithmic, okay, in space. And so this problem is p-space. And the same thing is for validity and for logical implication, are all variants of the same. Okay, very good. What about synthesis? Okay, synthesis. We have X and Y. X controlled by the environment, Y controlled by the controller, by the agent. Okay? What we want to do? We want to find a strategy for the agent such that for any possible value of the environment, okay, in the history, okay, it will tell you how to react to the history so far so that the formula is true. Okay, the NPL formula is true. How you compute this? Well, first you compute the non-deterministic automaton. Now you need to determinize it. Okay? This step is crucial. You cannot avoid determinization. Once you have determinized it, what you get a game. And on this game, you play for reachability. Okay, reachability, adversarial reachability. So reach it in spite of what the other do. Or it does. And we cannot avoid determinization because remember that non-determinism in automaton, it's a very strange thing. Because non-determinism, it's an angelic non-determinism. Okay? So it's essentially what it means. You have the power to foresee the future. This means angelic. So you see a fragment of your trace, but you see into the future, and you know the entire trace, and you know what path to get. Okay, so this is the non-determinism of automaton. Now, you cannot give this power to the agent, and you cannot give it to the environment. Okay, but here there are only two players, so if you want to keep it, you either have to give it to the agent or to the environment. But in both cases, you are doing something wrong. If you give it to the agent, how come that the agent knows the future? If you give it to the environment, well, now you are a little bit too defensive because you are thinking that the environment can see the future in order to decide what to do next. Okay? And so you are now a little bit too defensive as an agent. So you cannot do it. There is nothing to do. You have to transform it into a deterministic automaton. Once you've done that, you have a game. A game essentially, it's like a transition system in which you can distinguish the move done by the agent and by the environment. And you can compute a simple fixed point computation that actually will give you the solution in a linear time. Okay, in linear time in the sides of this game, which is double exponential in the side, so the formula in the worst case, but often is very small. Let's go back to planning. If we go to planning, we have now planning with non-deterministic domain. The fundamental observation is that this non-deterministic domain, if you transform it into automaton, they are deterministic. They generate a deterministic automaton. Because in order to do the transition, the automaton needs to see what the agent has chosen and what the environment has chosen. Okay, and so we have that the non-deterministic automaton is actually translated in a linear time into a deterministic automaton, the non-deterministic domain. I think I'm going to skip here. There are some examples. I think I'm going to skip it. Okay. So now I can give you, using the theory coming from synthesis, a very good algorithm for computing planning for temporally extended goals, for arbitrary LTL and LDL formulas over finite traces. The algorithm is the following. You give me the goal. I transform it to an automaton. I determinize it. Now I'm double extiming, but notice, double extiming what? In the goal. The goal is small. I'm double extiming at most in that. What about the domain? I didn't put it in the assumption, so it's not part of the formula. I kept the domain completely separate. Now, I'm using the domain, which can be transformed into a deterministic automaton in linear time. You have just to scan it. Okay, and I'm doing the intersection of the formula. So notice that the domain has not been changed. Okay, and now I do my game, which is the little fixed point computation. As a result, I am still X time complete in terms of the domain, and I am double X time complete in the goal. Now, why this is so important? Because the domain is big and the goal is small. And we essentially didn't touch the domain. By the way, this X time complete in the domain, if you describe the domain in PDDL, so if you describe it in a logarithmic way, because if you describe it explicitly, it's linear time. Okay? And so essentially this means that we can scale on planning domain, we can scale planning to have arbitrary small LTL formula. Now, this idea has been extended in many ways, and this idea of taking these formulas and then transforming into automaton and then manipulate the automaton and the domain and the automaton. You can do the same thing by manipulating automaton and MTPs, and you can make the domain non-Markovian by considering the domain formed by automaton. Many possible developments that are using this connection between these logic on finite traces and standard automaton. And by the way, remember that the algorithm for determination of standard automaton is the one that you have done at school, okay? And it's actually fantastic. It's one of the best algorithms we have. Okay, although it's exponential, it's actually very practical because it can be done on the fly. You only need the current state, and from the current state you can proceed. So it's a very well-behaved exponential algorithm. Okay, it's exponential, but it's very well-behaved. Okay, how I'm doing with time? Terrible, right?
Yeah, you have like 10 minutes. 15.
Okay. Okay, I'm going to tell you this that is funny, and then maybe I'll skip the rest. Now we're going to use this idea of having a formula for describing properties, and the fact that it can be translated into an automaton, and the fact that an automaton is essentially an MTP, deterministic, an easy case of MTP, okay, where the reward is when you get to the final state. And what I'm going to do, I'm going to look at Star Wars. In particular, I want to look at this particular device in Star Wars. This thing is called restraining bolt. You put it in a robot, you as a pirate put it in a robot that you have stolen, okay, to avoid that the robot escapes. So essentially, this restraining bolt controls the behavior of the robot, okay? Now, this thing is pretty interesting, how they come up with this. Probably they come up just from naiveness, but in fact, it's very interesting what they say. Because these restraining bolts are used on several agents. Look. So they cannot rely on the internals of the agent, because they need to be applied to several agents, okay? And these are pirates, right? So how it's not that the company that produced the robot would say, okay, if you put a restraining bolt in this way, you will control it, right? It's not going to be like that. So essentially, they cannot rely on the internal of the agent, and there is something more. We now live with two representations of the world. One representation coming from the agent, okay, and one representation coming from the restraining bolt. Are these two representations aligned somehow? No. One is used by the pirates, the other is used by the engineers, right? They are not aligned. So, But is there some form of alignment? In fact, a form of alignment exists. And the form of alignment is the real world. So both these descriptions are talking about the real world. So when you act in the real world, something will happen in the two representations, okay, as they monitor the real world. So they are synchronized somehow on the real world, okay? And now let's look at how we can handle this restraining bolt in using reinforcement learning. Okay, we have classic reinforcement learning. Okay, classic reinforcement learning, notice it's a synthesis problem somehow, because you have an agent, you have an environment. Okay, you are collecting data from the environment and the answer to the agent that the agent has to its moves. And out of that, you build the policy for the agent. And what is the policy? The policy is the strategy. Exactly like in synthesis, except that the strategy is typically a little bit simpler, because it's a strategy that says from the current state, I will do a certain action. Now, why this strategy? So the strategy should be from the entire history. Well, there is a theorem here that says, if your rewards are Markovian, this is all you need. Okay, you don't need to remember the history. There is a theorem that says that, otherwise this would be wrong. Second ingredient are this logic that we have just seen, this temporal logic of finite traces, and the possibility to transform them into automata. The fourth ingredient is I can do the product of one of these automatons and an MDP, and what I get, it's a new MDP in which the rewards are given by the automaton, and the dynamics is given by the MDP. Okay? Obviously change it because it's a Cartesian product of the two things, but in particular, since the automaton is deterministic, they don't change the probability in any way. The automaton don't change the probability in any way. I'm skipping it. So here is an interesting problem that can be solved. An interesting problem is the following. I have a learning agent, okay? This is like a reinforcement learning agent as the one that you read on the books. It uses certain features, okay? These are the representation of the state. Maybe in a fancy setting, these features are even learned through deep learning, okay? You don't even know a priori what are the features you are interested in. That's fine. The point is that I don't want to know about this feature in general, okay? As a human, especially if they come from deep learning, etc., these features might not be understandable to me. Also, even if they're understandable, they are typically the value of the sensor of a robot, right? So the value of the sensor are not really intelligible in terms of concept, okay? They're very low level, and that's fine. I like that. Now let's go to the restraining bolt. The restraining bolt is given in formulas, okay, over a certain language. This is a completely different story now. Who's writing this formula? Humans. They are not a learner. They are written by humans. Well, obviously they need to be understandable to humans, otherwise they cannot write it. And they use this alphabet L, which is disjoint from the alphabet of the learning agent. Okay? So I'm giving reward to the satisfaction of each of these formula. However, this reward, okay, so however, sorry, the feature that I'm using to write this formula are not the feature that I'm using in the learning agent. They are separate features. Okay, two representations, the restraining bolt, the pirates, the learning agent, the engineers. And I want to learn a policy. This time the policy must be non-Markovian. Okay, why non-Markovian? It is required. My formula is a temporal formula. The current state will not tell me enough about what is needed for the formula. However, how can I solve it? I can reduce it to standard reinforcement learning on standard and known MDPs. Okay? What I need to do, I need to remember the state of the formula. Now notice, given the formula, deterministic automaton, minimal deterministic automaton is unique. There's no less information that you can have in order to keep track of that formula, okay? So this is the really minimal. And minimization automata is polynomial. So what I'm going to do, I'm going to add to the feature of the agent the state of the automata, okay? Or the value, I can have many of them. If we have one, only one state of the automata, okay? And then I will have the action coming from the agent, transition and reward unknown, okay? Observation, the language L, the alphabet L that I used for writing the formula does not appear here. So you can learn the LTL formula without understanding what it says. Okay, because the alphabet is not there. You cannot reconstruct the formula in any way. Okay, you don't have the data to reconstruct the formula. And obviously, this is really somehow an important point that is related to this idea of having safety guarantees over things that you do with reinforcement learning. Here, the safety is you can guide the reinforcement learning to learn to be compliant to the formula, essentially. But there are many other works that does this. Okay, I think I have to close, but I just want to give you two slides. One slide is this one. When we go to first order representation, I want to go to first order representation for all of this. When we go to first order representation, you are now using models for describing things that are relational. Okay, and actually there are very good models to describe things. For example, for describing data, you can use UML, you can use ontologies, you can use entity relationship diagram. For describing processes, okay, the sequencing of activities, you can use one of the language that has been advocated lately for describing process, for example, BPM, okay, or activity diagram in UML. So you can be you can get guided by software engineer in how to do this knowledge representation, this conceptual representation. You also need some sort of glue, okay, so that somehow in this process what is missing are the connection with the data that are over here. And this connection, there's some literature that talks about this, can be captured through a notion of artifact. Essentially, the artifact, in poor terms, can be thought as state variable, actually variable, auxiliary variable for the process, okay, that connects information the process has with information available in the UML class data. You can think of it as a database. Now, if we are in this kind of setting, analysis, it's terrible. Formal methods tell us we don't know what to do. Why? Because it's an infinite state system, okay? All the possible configuration of the UML class diagram, okay, the instantiation of the UML class diagram, all possible configuration of the value of the artifact. So, in spite of describing it in a simple way, the dynamics that the system generates, it's very complex. And here there is a result coming from knowledge representation. This is my last slide. That I think is very important. And this result is about what can be said, what can be called bounded first-order state representation. Bounded. Bounded means that the object that I need to describe, to keep track of, in order to talk about my state, are in each moment finite. Finite and fixed, 10. Okay? They can change over time, arbitrarily. In each state they can be different, but at most 10 at each state. And to have an idea, it's like saying that your data are stored in a bookshelf. Okay? In your bookshelf, you can put all the data you like. However, your bookshelf has a certain capacity. After a while, you cannot put more data unless you remove some data. Now, if you have something like this, a very important thing happens. You cannot accumulate infinite information. Okay? Along this transition system, even if it's huge, you will never accumulate infinite information. Okay, obviously, if you consider collectively of the state, yes, information is infinite. But at each moment in time, there will be only finite information that is needed in order to continue the process. Now, if you have this, this result, then there are many interesting consequences of this. So model checking of arbitrary Mu-calculus formulas. Mu-calculus is a very expressive logic that in the propositional case is much more expressive than LDL and LTL, CTL, CTL star, etc. This is the king of the temporal logics. It's decidable. So model checking for full Mu-calculus is decidable, in spite this is first order with quantification across. The decidability, and the same thing is true for LTL if you don't have quantification across. Interestingly, if you have quantification across, it's not the case. And indeed, we have some secondary result here that says that in the first order case, you cannot capture full LTL in Mu-calculus with quantification across. And this result of decidability applies to very standard knowledge representation formalism like situation calculus. Okay, the one that you study in the books, right? That one. It's data-aware processes, dynamic system built over databases, dynamic system built over ontologies. And I'm finishing here.
Okay, so let's start the speaker first. We're over time, but I don't know if there's time for some quick questions. Or we can also talk to the speakers after, in meetings afterwards, after the talk.
So let me recap very quickly this sort of.
Quick question. No, yeah, go ahead. Recap.
Okay, let me recap. We want to put AI in dynamic systems. Okay, dynamic systems, real dynamic systems. And in order to do that, we are relying on certain things coming from AI planning, but also things coming from formal methods. And the synergies between these two things is actually crucial in order to get a level of generality needed to talk about this kind of things. The same thing, we didn't have much time, but the same thing is true when you live to first order logic. When you live to first order logic, again, you want AI to help you, reasoning about action, logic representation to help you. But also you want to connect to databases and processes. Okay? And you need to live to first order logic because things cannot be described propositionally. If you need to talk about object, you need to go to first order logic. And this is the reason why ontologies are based on first order logic, UML is based on first order logic, entity relationship diagram is based on first order logic, because you need to talk about objects. Okay? And here there are a set of results, okay, that still need to be exploited fully that are telling you that you can do this strip. Okay, you can start from the problem, go to each of these techniques, integrate them in a certain way, exploit synergy to study things that are unclear in one or the other, weaknesses that are present in one or the other, and get really a sort of a step ahead in what knowledge representation can be nowadays.
I have a very quick question. So I know you just got a very large European project to develop this.
Yeah.
Is that developed only a theory, or you have an application domain in the...
So in the grant, what I'm going to have, so essentially it's basic on theory. Mm-hmm. Okay. However, I'm going to have 3 parallel tracks on application. One in business process, one in Internet of Things, smart spaces, and one in manufacturing. And each of them will develop their own things, but they will use the result coming from the theory to try in practice how certain things work how certain theoretical things that work theoretically works in practice.
Industrial partners or with our university?
So the grant is given to a person. Okay, so it's me. Okay, and then I'm involving many groups in my department, also collaborations with external. Okay. But they don't get in money.
Okay, so any other questions? Oh, we have a question.
Your models that combines the model-based and model-free framework is very interesting for me. But for the models, you said you just considered all the environments as fully observable. So, for example, for each user, the environment is only exclusive to this user as an agent. For other users, they will not be able to see whatever is the environment of this user. So in each user's perspective, the environment is not fully observable because they don't know what is happening in other users' environment. So what do you think about this?
So if you analyze your words, there are a lot of interesting things. So you are talking about an agent that is immersed in a world with many other agents, and there is somebody that knows all the agent and all the environment. So now, every time that you have an agent, this agent is the projection of this knowledge that this big guy has over everything. The engineer, he sees everything. Okay, so this is a third-person view of the world. But now move to the agent. Okay, to the agent, all the rest does not exist. The engineer does not exist. So thinking that partial observability is the key is somehow biased. So it tells that there is somebody else that knows more, right, than the agent itself. I think that it's interesting to explore the case in which this is not the case. You are talking first person. You are the agent. There is nothing more that you can know except what you know. Right? Nothing else. Now, in this case, if you postulate the existence of hidden variables, notice you are postulating them because there's no way for you to know that this is true, right? And here, I think that in many cases, you want to remove these postulated variables and instead use non-Markovian description of what has happened so far, okay? So often these hidden variables are used to be able to talk only about one state. Don't talk about one state, talk about the entire history.
Thank you.
Okay, so I think we need to end. Let's thank Giuseppe one more time. I think there's a meeting that he has to go into a room like right now. So thank you. And if you want to meet with a speaker, you can talk to Carrie Lau or Peter.